Hello, I'm Dave Baring, Technical Director here at TriStar, and welcome to another Tech Talk. Today we're going to be talking about high-performance materials. And if you've had a chance to see our basic Plastics 101 session, you'll remember some of this information from that little seminar. But just to do a recap, plastics are broken down into a couple of different categories. First of all is commodity plastics, which are what we categorize the Home Depot plastics. These are materials that are good up to about 200 degrees Fahrenheit, and they have their own good attributes, but they are on the low end of the temperature scale. The next category is engineering plastics, which would be materials up to and just slightly over 300 degrees Fahrenheit. And then finally, the products that we're going to talk about today, which are high-performance materials. These are the materials that are 300 degrees and up, including some that will go as high as 1100 degrees short term. Plastics can be broken down in a couple of other ways as well. First of all, there are thermoplastics and there are thermosets. The category that we're talking about today, high-performance materials, is unique in that some of these materials can be either or. And we'll talk about that as we get further into our discussion. And then finally, amorphous versus crystalline. The same thing holds true here. The category of materials we're talking about today can be either or. Amorphous is materials that have a see-through quality. When you're talking about the high-performance materials, that see-through quality generally tends to be more of a translucent quality rather than a glass type see-through. But fact of the matter is you can see through amorphous materials in any category, 200, 300, 400 degrees and up. And then the crystalline products, which are the materials that are more of our structural materials that have higher physical properties at high temperatures. So as we start to take a look here, let's review again our plastics triangle, our food triangle here. And if you see here, we've got HPM circled. These are the materials at the top of the heap. These are the materials that are the top performers in the plastics world. We're going to be talking about each of these individually, but as a rule, all of these materials have some very similar properties. First of all of these materials have excellent service temperatures, as I mentioned, of 300 above. In fact, most of these materials are 350 and above, and I would say a good number of them are actually 400 and above. But for purposes of categorizing these, we say 300 and above falls under the high performance category. All of these materials have excellent retention of rigidity and creep resistance at elevated temperatures, and that's very important, especially when we start talking about structural integrity at temperature. Most of these materials also have excellent dimensional stability. Their coefficients of thermal expansion are fairly low in comparison to other engineering and commodity type plastics. Most of these products have pretty good chemical resistance. A few having outstanding chemical resistance, PTFE or Teflon being one of this category. PEEK, also PPS. These materials all have very, very good chemical resistance. The high-performance materials tend to have fairly good hydrolysis resistance, although there are some in the imidized category that you have to be a little more careful with when you're talking about exposure to things like steam or hot water service. These products all have pretty good X-ray and gamma radiation resistance, and then they all have outstanding flammability ratings, most of them VO, 94 VO ratings, and along with that comes limiting oxygen indexes are very good. Flame retardancy is pretty good. So these are all inherent to these types of materials as compared to commodity or engineering plastics. Let's start at the very top of the heap. We're going to start with the Cellazole material, which is PBI. PBI stands for polybenzimidazole. This is the highest temperature plastic material on the market today. This product can routinely operate in the 600 to 700 degree range in air. I must clarify that. That is in air. Service hours of 20,000 hours, 30,000 hours in those kinds of environments, not a problem. You can, in fact, take this particular product short term to temperatures upwards of 1100 degrees Fahrenheit. Pretty impressive for a plastic material. The key, again, to the high performance materials is that across their entire temperature spread, these products tend to maintain very high strength and rigidity, which translates to creep resistance. And as a structural component or a bearing component, you certainly want that. Their hardness doesn't change very much from, say, 300 degrees to 600 degrees. So that's something that's very dependable. The thermal expansion rates are very low as compared to most engineering and commodity plastics. PBI without a filler and without an additive actually has outstanding wear and frictional properties. Not as good as some that might have PTFE additives or something like that, but obviously in an application where you're running at temperatures in excess of 600 degrees, the PTFE component would be non-participating in an application like this because the PTFE would dissipate at a temperature lower than what the PBI can function at. So as an unfilled material with no additives, no lubricants, PBI has pretty good tribological properties. The dimensional stability on this material, the coefficient of thermal expansion is 1.3 times 10 to the minus 5, which is very, very low for a plastic material. And that dimensional stability is maintained across the majority of its temperature range. So that coefficient of thermal expansion rate, unlike some materials, especially PTFEs, does not change. It stays stable across the entire operating temperature range. Excellent resistance to high gamma radiation exposure. And in applications where you're looking at very high-end scientific applications, the PBI is a good application for that type of environment. High temperatures, low thermal expansion rates, high gamma radiation exposure. Has excellent dielectric values and also thermal insulating values. Again, across its entire temperature range. This particular material, as with most of the Amines, has a very low ionic contamination level. It's a very high purity material, just inherently. As a result, it's also very good as a low outgassing material in vacuum. So in areas such as in the semiconductor world, PBI for those 700 degree applications is a very good candidate for things like CMP rings and screws and things like that that are used in vacuum service at very high temperatures. Is okay. It's not as good as some other materials, but it's something that needs to be looked at on an application by application basis, as well as its moisture exposure. Again, the imidized materials tend to be fairly hydroscopic in certain conditions. Most of the imide materials really function best in hot air type conditions. So that's the primary characteristics of the Cellazol PBI material. The Cellazol product is something that's available from Quadrant, one of our partners, and it's also available in other forms in terms of new alloys that are available on the market now. Cellazol is being blended, for instance, with PEEK to make what appears to be an outstanding wear material compared to other polymers. So there are some things going on with the Cellazol outside of just unfilled compression molded grades, and something to look forward to in the future. Some of the applications for the Cellazole are very similar in all of the high-performance materials. In fact, you'll see as we go through these slides, they're very, very similar. The only thing that is different is the temperature ratings. Pump components, bearings, bushings, slide components, vanes for compressors. All of these are very typical applications for these types of products, again, where temperature is the driving force. So as we go through these, you'll see very, very similar, not only properties, but also similar application. The next product is polyamides. And polyamides are primarily known in the world by DuPont's trade name of Vespel. Polyamide is a condensate polymer. It is something that is made up through a process of what I like to call brewing. It's not unlike going to a brew house at Anheuser-Busch and seeing how they're taking, one product and pulling out certain things and then adding something and pulling out more things. And in the case of a condensate polymer, especially in the amides, what we're pulling out is alcohol and water, which makes the imidized material so unique in that if you reintroduce alcohol or water in a boiling state, you can and will in fact cause that polyamide to disappear very quickly. And I can speak from personal experience on that, where $3,000 bearings were put into an application where we were not fully informed that there was in fact very hot water involved in the system. So polyamides are, of course, unique in that they do have very high temperature ratings. They come in various forms. There are graphite fills, there's graphite Teflon combinations, there are moly fills, all with very distinct applications. But as a rule, the polyamides are 600, 550, 650 degree operating temperatures. Short-term excursions a little higher than that. There are both injection molding grade polyamides, which would be lower temperature, of course, but there are injection molding grades. There are what are called isostatically molded stock shapes, which would be rods and tubes and sheet. There are compression molded stock shapes. So the amides are very diverse in terms of processing and also in terms of blends that are available to do different things. The big advantage of the polyamides obviously is long-term temperature operation. One of the probably most famous applications of the Vespel material is on jet engines, where they are used primarily as, in fact have been used for years as the stator bearings on the turbine blades on jet engines. One of the most complicated applications for a polymer ever, because it's introduced to so many different variables: high temperatures, high vibration, very, very high cyclical rates on that vibration, a lot of harmonics going on. The polyamides are the only thing that hold up in that kind of environment. So tough material, very diverse in terms of what's available in compounds, also diverse in terms of how it's made, compression, isostatic. It can also be direct formed, which means basically a net finished part made out of a mold, and then injection molded. So again, extremely diverse material. Now DuPont's Vespel, like I said, is probably the most common trade name. Saint-Gobain has their product called Meldon, and there's a whole family of Meldon products. There's Meldon 2000, 3000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000. There's a whole family, all different. They're all polyamides, but some have variations, additives, processing techniques are different. So again, a lot of diversity here, but the bottom line is the polyamides all have very similar things as the PBI, the Cellazole. excellent thermal stability across their entire operating range, low thermal expansion rates, good inherent wear properties with or without additives. The fact that we can put graphite and PTFE in polyamides just makes it that much better. The polyamides tend to be a little more ductile than the cellulose products, so from a machining standpoint, they are a little easier to handle. Operating temperatures, again, 600, 700 degrees short term. Sometimes you can have little, even shorter term excursions up to 900 degrees. Strength to weight ratio is outstanding with the polyamides. It's good dielectric material. So, again, great diversity, great number of available compounds from different sources. Quadrant has their Duratron product. Ensinger has their Syntamid product. There's a lot of other manufacturers of polyamides, all different types of processing behind it, but polyamides are, for the most part, polyamides in terms of their capabilities. Again, the downside, though, hot water. It'll kill it. The next material in this high-end category, the imidized materials, is polyamide imide, which is best known as Torlon. Now, Torlon is a product from Solvay and Quadrant. Quadrant is the primary producer of the Torlon materials in stock shapes. This product is another one of those unique materials that can be in either the form of a thermoset or a thermoplastic. So that means it can be molded and extruded into a stock shape as a thermoset and then machined into a finished product, or it can be injection molded. The Torlon is a little bit more difficult to injection mold, and a lot of times you have to do post-curing depending on the part geometry, but it is something that is available out there if you have high enough volumes to justify the tooling. Tooling on these types of materials is going to be pretty expensive because the melt temperatures are extremely high. So just keep that in mind if you're thinking in terms of, I need 5,000 of something. The tooling may not justify 5,000 of something. If you got 500,000 pieces and Torlon is the right call, then you can certainly justify the tooling in that situation. But Torlon, as with the polyamides, comes in a lot of different varieties. There are several new bearing grades. There are a number of glass fills that are for structural components, also for dielectric components. Torlon, as a rule, has some of the best wear properties. If you've gone to the dentist and listened to that drill spinning at 300,000 RPM, the retainer that is used inside of that little bearing, inside the drill, is in fact being driven on a Torlon 4301 retainer, ball retainer. Very, very difficult application. What makes it even more difficult is that each time they sterilize that, again, talking about an imidized material, that exposure to steam starts this very slow process of breaking that imidized material down. So as a result, these bearings are a limited lifetime. In fact, I think the rule with the dentist is after 200 sterilization cycles, they pretty much have to replace the bearing or rebuild the bearing at least. So again, imidized materials, that's something you have to be aware of, but in dry, unlubricated, high speed, high load, very difficult applications, high PV, we're talking about capabilities here in PVs of tens of thousands, hundreds of thousands, and in lubricated applications even as high as 2 million PV with some of the Torlon grades. Typical applications, like I said, bearing retainers, bushings, speaking in terms of bearings, grommets. We have some applications in satellite systems where we're using it for grommets. There are compressor applications for vanes and bushings, so very, very diverse material, but again, looking at it in terms of its tribological values, its thermal stability, its strength, and the retention of strength over its entire temperature range. This is the standard theme when we're talking about these high-performance materials, especially the imidized products. Now the next material on our list here is going to be the PTFEs, and we've done a couple of other seminars on things like Rulons, so we're going to talk in general about PTFE. PTFE, or polytetrafluoroethylene, is a fluoropolymer, and it is only one of a number of materials that fall into the category of fluoropolymer. PTFE is kind of unique in that it starts out as a granule. It's almost a talc-like powder in its original form. And what makes it unique is that the way you process it is you have to take that powder and essentially compress it at a 3-to-1 ratio. So if you want to make 1 foot of Teflon rod, you have to start with 3 feet of resin. And then you have to take that material and cook it or sinter it. And that's where PTFE gets a little tricky, because the way you can judge quality of a PTFE material is going to result in how well that material was pressed and how well that material was sintered. It doesn't take much to screw it up. So when we talk about selling the Rulon materials or fluorescent or ultraflons or things like that, we do so with the knowledge that these products are being made with the highest standards. And that's what's really critical when it comes to PTFE. There's a lot of stuff out on the market out there. But to get the best wear value, to get the best frictional value, the strength, it comes down to things like crystallinity. How crystalline or amorphous is the PTFE, because that has a big bearing on how well that material performs. PTFE is used primarily for seals and bearings and gaskets. Those are the 3 areas that we see the most application. PTFE by itself is a lousy bearing. And the invention of Rulon back in the early 50s was a result of that knowledge. PTFE is a great gasket, because with a gasket you want it to cold flow, and that's the problem with PTFE, is that without reinforcement of some form, it will cold flow, and it will do that at room temperature. You can take a slug of Teflon rod and stick it on a table with a 2-pound weight on it and come back in 24 hours at room temperature, and it's going to be different shape. It's going to actually deform considerably. It doesn't take much. And what makes PTFE really interesting and unique is that it actually of 78 degrees Fahrenheit. And what makes that unique is the fact that Teflon can operate, or PTFE can operate from -400 to +550, but it actually has a transition temperature of room temperature. So where all of these other materials come into play is the fillers. So all of the PTFE products that we work with are going to be filled with any number of different compounds. Glass fibers, carbon fibers, graphite powder, coke flour, polyester. There's all kinds of different things, minerals that are used to fill, and each one of those fillers has a pretty defined logic behind it. Some of it's for physical strength. Some of it is for improved dielectric value. Some of it is for heat or electrical dissipation. So the fillers have a real purpose. Another unique thing about PTFE is that sometimes the colors that you see, like the trademark color of maroon for Rulon AR and LR, that maroon color, if it were not there, would completely change the performance values of those 2 materials, because that additive, that color additive, is actually a metallic oxide. And when you put a metallic oxide into a PTFE, or any plastic for that matter, it does act as a wear inhibitor. So there's a big difference between a uncolored and colored version of the same filler. Kind of a unique little thing about PTFE. Some of the general properties of PTFE, as I mentioned, minus 400 to plus 550. We have some materials that will go to 600. There is a new material from Quadrant that will even go as high as 700. Yes, that's right. PTFE that'll go to 700 degrees. So there's a lot of unique things available out there in new compounding that are even further enhancing the capabilities of PTFE. Chemical resistance, it's essentially inert to anything in the chemical world. The exception is molten sodiums. And in fact, molten sodiums is what we use to etch PTFE products so that we can bond it to another substrate. Does not absorb water, completely zero absorption, so that's a good thing when you're trying to design especially bearings and seals. What makes filled PTFE interesting is that you can really control the amount of flexibility and stiffness by percentages of additives and the shape of additives. There's so much diversity. There's hundreds and hundreds of different filled PTFE versions out there. Offers a great amount of diversity for us as designers of seals and bearings. The thermal values of PTFE will kind of go all over the board. It depends on the fillers. Teflon by itself or PTFE by itself with no fillers, very high thermal expansion rates. If we're looking to design a bearing, for instance, at the highest temperature rating, then we're going to look for something in terms of a filler that will give us the best thermal expansion resistance that we can get. Applications, again, as I said, seals, bearings, gaskets. That's really where PTFE shines. It's also a great dielectric insulator. It's a great thermal insulator. So these are some areas where filled Teflons, the Rulons, the fluorescents, the ultraflons, these are places where this material really, really comes through for you. Next we're going to talk about is PEEK. Now PEEK, polyether ether ketone, is a product that comes out of Victrex. There are other versions of PEEK on the market now, but PEEK, like all of these other polymers, is highly compounded. We have traditional fillers like glass fibers, carbon fibers, combinations of carbon fiber and PTFE, graphite powder. Every time we do this to a polymer, we're basically trying to enhance the properties of that polymer. The unfilled version of PEEK is now not only FDA approved, but it's also got a USP 6 classification, which means it's implantable grade now. There's a whole new family of life science PEEKs that are available out there on the market. But for the most part, we deal with 4 primary compounds. First is the unfilled, and this is a version that we would use sometimes for things like blades on rotary compressors, for instance, where we want the durability and the physical strength of the PEEK, but we also want the ductility of that material so that it is capable of withstanding a lot of misalignment or possibly deformities in the mating surface. So virgin PEEK is a very good candidate for that because it has inherently very good wear properties and also very good low friction properties without any additives. You put carbon fiber in and now you've dramatically increased the strength of the material. You've also given the material thermal dissipation capability. You've also given it a much greater stiffness, much lower thermal expansion rate. So a lot of big important values in terms of using this material as a bearing grade product, but also as a structural component. The classic bearing grade PEEK is what's called HPV, or bearing grade 10-10-10, which is a combination of graphite powder, carbon fibers, and PTFE. So you have the additional strength of the carbon fibers, and then you have 2 essentially migratory lubricants in the graphite and the PTFE. And then finally we have glass-filled PEEK, and the glass-filleds are usually used for structural or sometimes for dielectric applications. Not so good for bearing applications because it tends to be a little abrasive, but still a very good material. 485, 500 degrees temperature range. PEEK, as a rule, has a pretty good chemical resistance. It's not quite as good as the PTFE, but certainly better than any other materials that I've talked about so far. Again, mechanical stiffness. It's got great properties across its full temperature range. Does not absorb moisture. So it's just got a lot of very, very important properties that if you are looking in terms of cost, we went from the imidized materials that are, for the most part, $550 and up. Now we've moved into a category of materials that is in the $400 to $500 range with PTFE and PEEK. Good cost effectiveness in terms of parts. It's injection moldable, it's extrudable and machinable, it's compression moldable, sheet rod tube. It's all types of formats, easily machined. And then with the injection molding, we can actually even extend some of the blending to change percentages. We can improve frictional properties. We can improve dielectric properties. We can improve thermal dissipation or electrical dissipation. So again, all of these materials all in the high performance category, great diversity in terms of how they are used. The last item on our list is PPS, which is better known as Riton or Tektron. PPS is what we at TriStar and a lot of people in our industry refer to as poor man's PEEK. Because if you have an application where PEEK seems to be the right call in terms of its temperature range, its chemical resistance, its wear properties, its physical strength, all of these things have been identified as key factors in your application, but the cost is too high, then we will sometimes direct our customers to take a look at the different available blends of PPS. PPS in bearing grades has very, very good wear factors, very low coefficient of friction in the right compounds. It's thermally very stable, good chemical resistance. The trade-off is here that you're giving up a little bit in temperature over the PEEK. But if you have an application where the engineering plastics are not cutting it, your Delrin is not working, your polyesters are not working, PTFE may be overkill, but PEEK has the physical strength that you want, chemical resistance, everything about it's what you want, but you're really only going to be working at 400 degrees. That's where the PPS comes into play. It's a nice tweener, as we call it. It's in between the engineering plastics and the higher cost high performance materials. Very, very good material, very diverse, and again available in extruded, compression molded, or injection molding grades. So if you have high volume applications for small bearings or structural parts, very good candidate for that type of application. The PPS, you're basically looking at half the cost, maybe even more than half the cost of the PEEK at the resin level. So something worth taking a look at and considering as you look at the big picture of high performance materials. These are the materials that we work with a great deal here at TriStar. I've tried to stress the diversity. All of these materials are at the high end of cost, but they're also at the high end of performance. And like anything else in life, you get what you pay for. And that's certainly true with plastic materials as well. So I hope this gives you a little bit better picture of where high-performance materials come into play. Again, great diversity and great availability. These are materials that we work with every day, and we would invite you to contact us again at the website www.tstar.com. Go to our Ask the Experts, join our blog. We have a lot of different angles for you to be in touch with us, and we certainly invite you to do that. And if you have any questions or have some applications where high-performance materials might be your candidate, we look forward to your questions and look forward to working with you. Thanks again for joining us, and look forward to seeing you on another Tech Talk.